Welcome to the Deep Dive. Today we are plunging into an invisible world, a world of electromagnetic waves that reveal really the secrets about our physical reality, about motion, and now even about our health.
We're talking about radar.
We are talking about radar. But you should probably forget the flickering green screens from old movies, the big bulky dishes.
That's right. I mean, people hear radar and they immediately think air traffic control or fighter jets. But the stack of sources we've got for this deep dive, it just confirms that radar signal processing is now the hidden intelligence behind so much of modern life.
It really is.
We're seeing it in, driverless cars, advanced planetary mapping, and even medical diagnostics.
So our mission today is, well, it's decidedly technical. We have this really densely packed collection of material sources covering the fundamentals, some really advanced signal processing algorithms, and the absolute cutting edge of machine learning integration.
And our job is to unpack it. Exactly. We're going to break down step by step how these incredibly faint electromagnetic echoes are processed and transformed into precise data points, things like range, velocity, and increasingly the actual identity of an object.
And I think to set the stage for all that technical detail, it's important to understand the sheer ubiquity of radar today. I mean, it truly underpins modern infrastructure in ways that might surprise you.
Oh, absolutely. I mean, beyond the obvious stuff, aviation, air traffic control, making sure commercial flights stay separated, you have this critical role it plays in the maritime world.
Oh, navigation.
For navigation and fog, providing essential coastal surveillance. It's fundamental.
And then there's the meteorological application. Doppler radar has fundamentally revolutionized weather forecasting.
In what way?
It doesn't just tell you there's precipitation anymore. It actually measures the wind speeds, the movement of storms in real time. It does this by analyzing the phase shift of the waves reflecting off rain and ice particles. And on the ground, I mean, the consumer-facing applications are just exploding. Automotive radar is the core eye of what we call advanced driver assistance systems.
The ADAS.
That's the tech that enables adaptive cruise control, the thing that keeps you spaced correctly on the highway. And of course, collision avoidance. It prevents accidents.
And we shouldn't forget the applications that probe, beneath the surface. Ground-penetrating radar or GPR.
Right.
This is just vital in construction, geology, even archaeology. It helps map subterranean structures, utilities, all without digging a single hole.
And then finally, when we look up, radar is how we map the topography, the composition of distant planets and moons. It's a technology that it touches every single domain.
So if it's everywhere, why is it so hard? Why do we need all this incredibly advanced processing?
That's the question, isn't it?
Right.
It all comes down to physics, and specifically the fundamental challenge of just detecting anything at all.
To really get a grip on the complexity of the processing, we have to start with the radar range equation.
Yeah.
This is the absolute cornerstone of radar system design.
Why is it so important?
Because it mathematically dictates exactly how much signal power you can expect to get back from a target. It relates the received power, we call it P sub R, to everything that matters. The power you transmit, P sub T, the target's characteristics.
That's sigma. The radar cross-section.
Right, sigma and the antenna efficiency, G. But the moment you look at the equation, one term just jumps out and completely ruins your day.
The range to the target, R, raised to the power of 4, R to the 4th. I mean, that devastating mathematical relationship is the primary obstacle every radar engineer is fighting against.
That R to the 4th penalty is the single biggest physics hurdle. You have to visualize why it happens. Imagine the radar transmits a powerful pulse of energy. As that energy spreads out spherically on its journey to the target, the power density drops off by R squared.
Okay, so that's just the outbound trip.
That's just the outbound trip. Now, when that energy hits the target scatters some of it back. But that returning echo, that tiny, tiny fraction of energy, it also has to spread out spherically on its way back to the receiver.
And that's another factor of R squared.
That's another R squared. You multiply those two losses together, and you get this catastrophic R to the 4th power dependency.
So if you double the range.
If you double the range, the received power drops not by a factor of 4, but by a factor of 16.
That is just brutal. It makes you realize why these high-powered systems are so necessary and why the signal processing gain is so critical.
Our source data has a staggering illustration of the drop-off. You start with a massive transmitted power of 40 dBW.
Which is 10,000 watts. A huge amount of power.
10,000 watts aimed at a large target with a pretty generous radar cross-section of 10 square meters. At a relatively short distance, let's say 10 kilometers, the power you get back is already tiny. It's around minus 103 dB gem.
That's a fraction of a microwatt. It's almost nothing.
It's almost nothing. But now, if you stretch that range out to 500 kilometers, which is a very feasible distance for long-range air surveillance or space tracking, the received power just plummets. It drops to a minuscule minus 171 dBm.
Minus 171 dBm. That power level is buried deep, deep within the noise floor of any practical receiver.
And that is the fundamental challenge of the industry, finding that needle in a haystack. Every single technique we're going to discuss today, pulse compression, coherent integration, advanced algorithms, is fundamentally designed to claw back the energy that's lost to that R to the fourth law.
Okay, so how do we interpret those faint echoes once they actually arrive? We need the basics, right? Distance and motion. Distance or range is the simplest one.
It's just timing the echo.
Right. It's calculated using the round-trip delay time, t,
Right.
and the speed of light, c. So the formula is r equals c times t divided by 2. You have it because the pulse had to go out and come back.
Exactly. Now let's look at the parameters that define the target itself. The radar cross-section, sigma, is critical. And conceptually, sigma is not the physical size of the target.
That's a really important distinction.
It is. It's a measure of how much of the energy hitting the target gets scattered back precisely toward the radar receiver.
So a large, smooth, perfectly spherical metal object might have a high sigma.
Precisely. And conversely, you could have a physically enormous target, but if its geometry is specifically designed to deflect energy away from the receiving antenna,
Using angled facets or special radar-absorbing materials?
then its effective sigma can be tiny. And that's the entire premise of stealth technology. You're just trying to minimize the radar cross-section to make the target effectively invisible, even if you've managed to solve the R to the fourth problem.
And finally, we have antenna gain, GT, and GR. This is about how well the radar focuses its energy.
Gain is all about efficiency. It's a comparison to an imaginary isotropic radiator that just blasts energy equally in all directions. So if your radar has high gain, it means it's concentrating that precious 10,000 watts of power into a very tight, focused beam.
And that boosts both the transmitted power density and the receiver sensitivity in that one direction.
Right, which helps mitigate that R to the fourth power penalty before you even start the processing.
Okay, so once we know how far away the target is, the next essential piece of intelligence is how fast it's moving. And that brings us, of course, to the Doppler effect.
This is truly beautiful physics in action. It's just like the pitch of an ambulance siren rising as it comes towards you and dropping as it moves away. The frequency of the radar echo shifts based on the target's radial velocity.
And that's the component of its speed moving directly toward or away from the radar. We call that shift the Doppler shift, or F sub d.
A shift to a higher frequency, a positive shift, means the target is closing in. A negative shift means it's retreating. The magnitude of this shift is defined by the Doppler formula. F sub d equals 2 times VR times FC, all divided by c.
So what's important there is the relationship. The shift is proportional to the radial velocity, VR, but also to the carrier frequency, FC.
Exactly. So if you're using a higher frequency radar, say 10 gigahertz, which is X-band, very common for high-res tracking, you get a much larger, more measurable frequency shift, the same velocity compared to, say, a 1 gigahertz L-band radar.
Let's use that 10 gigahertz example.
Okay, with a 10 gigahertz carrier, if a target is screaming toward you at 100 meters per second, that's about 360 kilometers an hour, the resulting Doppler shift is approximately 6.67 kilohertz.
That is a very distinct frequency that a receiver can measure with extreme precision.
It is. And if it's moving away at the same speed, it's minus 6.67 kilohertz. It sounds simple, but the precision is phenomenal. We are essentially measuring speed by measuring these minute frequency changes in a multi-gigahertz signal.
And this leads us to the critical fact that underpins all the processing that comes next. If the target is stationary, a building, a tree, the ground, its radial velocity is 0.
Which means its Doppler shift is 0 hertz. And this distinction between 0 hertz returns and non-0 hertz returns is the basis for how radar systems separate the targets we want from the interference or clutter that we don't want.
Okay, so we know the power return is tiny because of r to the fourth, but we also know how to measure distance and velocity. Now we transition from the physics to the engineering. How do we take that faint signal and actually process it to get both high energy for detection and high resolution for clarity?
This is arguably the first major signal processing innovation you have to understand. It solves the great dilemma of radar design.
Which is,
You need high energy to fight that R to the fourth loss, which means you need to transmit a long pulse. But you need fine resolution to separate two closely spaced objects, which means you need a short pulse.
so it feels like a fundamental trade-off. A long pulse gives you good detection range but terrible resolution. A short pulse gives you great resolution, but you can't see past your nose because you haven't transmitted enough energy.
Precisely. If you only rely on pulse duration, you're stuck. Pulse compression is the elegant solution that breaks this trade-off. We transmit a long pulse, maintaining that necessary high energy for detection, but we embed a special signature inside it.
And that signature is often a linear frequency modulation, or LFM. Everyone just calls it a chirp.
A chirp is perfect for this. During the long pulse duration, which we'll call T, the frequency is deliberately swept linearly across a wide bandwidth, B, so it might start low and ramp up high, for example.
Okay, so the energy is distributed across a long duration and across a wide frequency spectrum. When the echo comes back, how do we get all that energy back into a short, sharp spike?
We use a technique called a matched filter. It's sometimes implemented as a correlation function, and it acts like an intelligent puzzle solver. The matched filter is tuned specifically to the chirp waveform that was transmitted.
It knows what it's looking for.
It knows exactly what it's looking for. So when the long, kind of messy received pulse is fed into it, the filter instantaneously aligns and sums up all the energy that was scattered across that duration T into a single, highly compressed, narrow peak.
And that moment of compression, that's the real payoff.
It is. The output spike now has the high energy of the original long pulse, but its duration is equivalent to 1 over B, the inverse of the transmitted bandwidth. This means the range resolution is determined not by the long pulse duration, but by the wide bandwidth.
The formula is delta R equals C divided by 2B. Let's look at how transformative this is, using the figures from our source material. If you use a narrow bandwidth of only 1 megahertz, your range resolution is 150 meters.
Which is fine if you just need to know which quadrant the target is in, I guess.
But for modern applications, like autonomous driving or specialized imaging, where you need to distinguish a curb from a pedestrian, 150 meters is useless.
Completely useless. Now, if you leverage pulse compression and you boost the bandwidth to 500 megahertz, the resolution tightens dramatically to just 0.3 meters. 30 centimeters.
We've maintained the long-range detection power, but achieved centimeter-level resolution purely through intelligent signal manipulation.
And the success of this technique is quantified by the compression ratio, which is just the product of the pulse duration T and the bandwidth B. A high TB product means you get a massive processing gain, which significantly improves your signal-to-noise ratio. This is the first essential step to making that faint -171 dBm echo visible above the noise floor.
So pulse compression gets us high-resolution range from a single pulse, but as you mentioned, radar needs two dimensions, range and velocity. To get velocity, we have to observe the target over a period of time.
This is where we create the range Doppler map. We're combining the range information from pulse compression with the velocity information from the Doppler effect.
And the process is a sophisticated 2D analysis based on the fast Fourier transform, the FFT.
Right. Step 1 happens immediately. The receiver performs range compression on every single received pulse. This gives us a stream of high-resolution range profiles.
And step 2 is the temporal analysis. We collect a sequence of these compressed pulses over a specific duration. We call this the coherent processing interval, or CPI.
The term coherent is critical here. It means that the radar maintains and tracks the phase history of the signal throughout the entire CPI. And phase matters because motion, that radial velocity we discussed, manifests as a predictable linear change in the phase of the echo across sequential pulses.
Ah, so you're not just looking at the phase shift in one pulse relative to the next, you're looking at the phase shift pattern across, say, 100 pulses.
Precisely. Once we have the data gathered in the CPI, we apply a second FFT, the Doppler FFT. We do this across the sequence of pulses for every single range band. This transform converts that phase progression into the Doppler frequency domain, which corresponds directly to the target's velocity.
And the final range Doppler map is this, well, it's a beautiful 2D plot. If you look at it, all the stationary objects cluster around the 0 Hz velocity line, and the moving targets appear shifted up or down, separated not just by distance but also by speed.
It's the visual heart of radar tracking. It effectively separates moving targets from the stationary background, even if they're at the exact same range. And just like with pulse compression, processing a large number of pulses, N coherently gives you a massive signal-to-noise ratio improvement.
That's the processing gain.
Right. It's calculated as 10 times the log of N. So if you integrate 1,000 pulses, you get 30 dB of processing gain, which is absolutely essential for detecting those extremely weak long-range targets.
The range Doppler map is great for visibility, but what if the clutter is so strong it just swamps the entire map? We talked about stationary objects like buildings having a 0 Hz Doppler shift. But often those stationary returns are thousands of times stronger than the moving target we actually care about.
The clutter problem is endemic, particularly for ground-based systems. If a small moving drone happens to be flying right in front of a massive, strong reflecting factory wall, the wall's echo will absolutely mask the drone. It just renders it invisible, even if the target is technically present on the map.
So we need a surgical way to excise those stationary returns without touching the moving ones.
And that is the role of moving target indication, or MTI. MTI fundamentally exploits the coherent nature of the signal. Stationary clutter maintains the exact same phase relationship between pulses.
Whereas moving targets, because of their Doppler shift, show that steady phase progression.
Exactly. So the simplest MTI filter, the two-pulse canceller, is elegantly simple. You just subtract the received signal from pulse N from the signal you received in pulse N-1.
If the echo is from a stationary object, the signals are essentially identical, and they cancel out perfectly.
Right, but if the echo is from a moving object, the phase progression means they don't cancel, and the signal for the moving target remains. MTI is therefore a high-pass filter in the Doppler domain. It effectively puts a notch filter right at 0 Hz.
That seems like a perfect solution, but I know there's always a catch in radar engineering. What's the big limitation here?
The catch is a critical operational hazard known as blind speeds. Remember, Doppler shift is based on phase progression. A target moving at certain specific velocities can, purely by coincidence, cause its phase shift to be an integer multiple of 360 degrees between pulses.
And if the phase shift is a multiple of 360, then the phase of pulse n is mathematically identical to the phase of pulse n-1.
Exactly. It's mimicking a stationary object. The MTI filter sees no phase change, assumes it's clutter, and cancels it out, making the target invisible. It's a blind spot in the velocity domain.
That's terrifying, especially for a defense or air traffic system. You have a crucial target moving at a specific speed, and your system just filters it out like it's a stationary building. How do engineers mitigate that?
The primary solution is to stagger the pulse repetition interval, the PRI. Instead of using a fixed time between every pulse, you randomly or systematically vary it. Since the blind speeds are dependent on the PRI, by changing the PRI, you change the blind speeds.
So a target at a fixed, dangerous speed can't simultaneously align with the cancellation condition for multiple different PRIs.
Correct, which ensures its visibility is recovered over the full CPI. It's a critical operational requirement for any MTI-equipped system.
Okay, we've now established how to find the target's position in range and its speed and velocity. But for true tracking, we need to know precisely where it is angularly. This brings us to the third dimension, the angular domain, and the shift from traditional mechanical systems to modern electronic arrays.
The old way of doing things, which is still common in some applications, was to use a single large parabolic dish that had to physically rotate to look in a different direction.
Slow, prone to mechanical failure, inefficient.
All of the above. Modern radar has solved this by moving to the phased array antenna, which relies on electronic steering through a process called beamforming.
This is a major engineering leap.
It is. Instead of one large physical aperture, we use an array of many small individual antenna elements, sometimes hundreds or even thousands, which are all fixed in place. The magic happens in the digital control system.
So how does a fixed array move the beam without physically moving?
It's all about phase manipulation. Think of the array elements as listening posts. A signal arriving from, say, 45 degrees is going to hit each element at a slightly different moment in time. This creates a tiny but predictable time delay, a phase difference across the array.
So we know exactly what those phase differences should be for an echo arriving from any specific direction.
Right. So we apply carefully calculated phase delays, or weights, to the signal received by each element before we sum them all together. We adjust these weights so that the signals arriving from our desired direction add up constructively. They reinforce each other.
And signals arriving from other directions or just noise, they add up destructively. They cancel out.
Exactly. This digitally focused summing process is beamforming. It means we can instantly point the beam to a new location just by changing the digital weights applied to the element outputs. The speed and agility are incredible.
And the benefits are transformative. Not only is the tracking much faster, but you can form multiple simultaneous beams.
A single array can allocate one digital beam to maintain a track on a high-priority target, use a second beam to search the whole sector, and use a third beam to actively suppress an incoming jamming signal by creating a null in its direction.
Let's consider a practical example, like the Uniform Linear Array, or ULA, which is common in things like automotive radar.
In a ULA, the spacing between elements is usually set at half the signal wavelength. This maximizes the angular field of view while preventing an artifact called grating lobes, spurious side lobes that can confuse the system. For a reasonably sized 8-element ULA, we might get an angular resolution or beam width of around 12 degrees.
Which is narrow enough for a lot of tracking purposes, but as we're about to see, it's not enough for complex multi-target environments.
Right. That 12-degree beam width is fine if your targets are far apart, but what if two targets are almost exactly aligned in angle? Or what if there's powerful interference coming from a direction very close to your target?
That's when conventional beamforming, sometimes called Bartlett beamforming, starts to fail.
It does. It just uses a simple delay and sum. It works, but the resulting angular peaks are broad. If two signals are closer than the array's beam width, they just blend into one big blob, making them impossible to resolve. This is the classical Rayleigh limit, the resolution limit based on the physical size of your aperture.
So to break that limit, we need smarter math. Let's start with MVDR, the minimum variance distortionless response, also known as Capon beamforming.
MVDR is the first step into the world of adaptive processing. Unlike Bartlett, which is fixed, MVDR is constantly adjusting. It frames beamforming as an optimization problem. The algorithm seeks to minimize the total output power from the array.
So it's crushing all the incoming noise and interference.
Exactly, while simultaneously enforcing a strict constraint. It must maintain unity gain in the specific direction we tell it to look. It's actively trying to listen only to what you tell it to, while pushing down everything else's noise.
The result is dramatically higher angular resolution than Bartlett and phenomenal adaptive interference suppression.
It is. If a powerful jammer suddenly appears, the MVDR algorithm can quickly adjust its weights to place a deep null in the jammer's direction, preserving the system's ability to track the target.
But that computational sophistication must come with a price.
It does. MVDR requires significant processing power because it involves calculating and inverting the received signal covariance matrix over and over again. This matrix inversion makes it slower, more computationally expensive, and crucially, more sensitive to small errors in the physical calibration of the antenna array.
So if MVDR is adaptive and complex, then where does music multiple signal classification fit in? I understand this is often called the gold standard for super resolution.
Music goes beyond adaptive filtering. It enters the realm of subspace processing. It is designed specifically to break that classical Rayleigh resolution limit.
How does it do that?
Instead of just processing the signal stream, it studies the entire statistical environment of the received data. It performs something called eigendecomposition on the signal covariance matrix, which mathematically separates the entire observed energy into two orthogonal subspaces.
So you have the signal subspace, which contains all the coherent energy from your targets.
And the noise subspace, which is composed purely of random noise and uncorrelated interference. It separates the meaningful structure from the background chaos.
And here's the clever part. The true direction of arrival vectors for the targets have to be mathematically orthogonal or perpendicular to the noise subspace. Music works by searching for directions that are perpendicular to that noise subspace,
Which gives you incredibly precise location data, even if the targets are spatially overlapping in a traditional plot.
Exactly. The output, the music pseudospectrum, displays these razor-sharp peaks corresponding exactly to the true directions of arrival, allowing it to distinguish signals that are much closer than the physical beam width should theoretically allow. That's why we call it suture resolution.
This really highlights the deep engineering trade-offs involved, right? It's not about finding the best algorithm, but the right one for the job.
Our source material has a great comparison summary. Bartlett is, complexity 1, super easy to implement, but its resolution is low, and it needs a robust 20 dB signal-to-noise ratio to work reliably.
Then you have MVDR, which offers a fantastic balance. Moderate complexity, much better resolution, and it only needs about 10 dB of SNR because it's so good at suppressing interference. It's often the sweet spot for practical, robust operation.
But if you're in a highly cluttered, low-power environment, you move to music.
Right. High complexity, but the highest resolution. And critically, because it leverages that statistical structure so effectively, it only requires a minimum SNR of 5 dB. Music can reliably detect and resolve targets that other algorithms would simply dismiss as random noise. The choice is always a balance between your budget for computational horsepower and the performance you absolutely require.
Okay, we've established how to get range, velocity, and angle with increasing precision. But the final, most complex challenge is interpretation. Classification. What is that echo? Is it an incoming missile, a benign drone, a large bird, or just a truck?
This necessity for instant identification has really ushered in the era of machine learning and AI integration.
And the key to integrating AI is transforming that complex electromagnetic data into a visual format that AI models, which excel at image recognition, can easily digest.
And we've already done most of the work with traditional processing.
You're talking about the range Doppler map.
Exactly. The range Doppler map is a 2D plot of power versus range and velocity. It is conceptually an image. Therefore, it makes a perfect input for convolutional neural networks, or CNNs.
That is such a radical shift in thinking treating radio waves like photographs.
Mhm.
How does the CNN architecture actually process this image of an echo?
The CNN treats the map, say, a 128 by 64 matrix, as input data. The initial convolutional layers are tasked with extracting spatial features. But in the context of radar, these features aren't edges and corners, they're the unique signatures of the target.
And what defines those signatures?
It's largely the target's microdoppler signature. This is the tiny velocity variation imposed on the main target echo by subtle internal movements, like a person swinging their arms as they walk, or the rotation of a drone's propellers.
So the main body of a target gives you the primary Doppler shift, but the moving components create these unique side lobes and streaks in the map.
That's the key. So if a car appears as one large solid velocity blob, a drone, because of those rapidly rotating propellers, might appear as a distinctive cluster of small, separated high-velocity streaks scattered around the main body's velocity.
And the CNN learns to read those specific fingerprints.
Precisely. In our source material, we looked at a test case where a synthetic data set involving 4 classes, pedestrian, car, drone, and clutter, was fed into a typical CNN pipeline.
And the performance was impressive.
Stunning. The model achieved a classification accuracy of nearly 99.5%. This just confirms that CNNs are superb at distinguishing these subtle differences in the micro-Doppler domain. The AI learns the complex geometry of rotation and movement patterns far faster and more reliably than any traditional rule-based algorithm.
So it's not just detecting movement. It's recognizing what is moving based on its characteristic kinematic signature. That's
Yeah.
a huge leap in situational awareness.
It is. But while CNNs are excellent for classifying an instantaneous snapshot, a single range Doppler map, the real world is dynamic. Radar provides a continuous stream of data over time.
So you need AI that can track historical movement, predict future positions, and classify activities that unfold over seconds, not milliseconds.
Which means you need memory. And in AI, memory means recurrent neural networks, specifically long short-term memory networks, or LSTMs.
LSTMs are specialized RNNs designed to process sequences of data, effectively remembering dependencies over long intervals.
Right. So by feeding a continuous stream of range Doppler maps into an LSTM, the network learns movement patterns. It's not just, is this a pedestrian, but is the pedestrian walking, running, or falling?
That ability to classify complex unfolding activities, human activity recognition, is critical for smart security and increasingly for healthcare monitoring.
The LSTM learns the typical phase shift sequence associated with the micro-Doppler signature of, say, a healthy gait versus the sudden catastrophic signature of a fall. It also allows for much more robust target tracking, learning, and predicting complex nonlinear maneuvers.
Now, switching gears, one of the biggest bottlenecks in training any of these deep learning models is just getting enough high-quality labeled data, especially for rare events, right? A certain type of stealth drone or a very specific jamming scenario.
That brings us to generative adversarial networks, or GANs. GANs are deployed specifically to tackle this data scarcity problem by creating synthetic yet realistic radar data.
So tell us how that adversarial process works. It sounds like a competition.
It is. A JAN involves two networks locked in a competitive loop. First, you have the generator network. Its task is to create synthetic, fake range Doppler maps, essentially trying to mimic the appearance of a real target's echo.
And the second network?
That's the discriminator. Its only job is to look at a data point, which could be real data or the generator's fake data, and classify it as real or fake.
So the generator's goal is to fool the discriminator, and the discriminator's goal is to never be fooled.
Exactly. This constant adversarial training process pushes the generator to create increasingly realistic stress test data. This synthetic data is then used to augment the real data sets, ensuring the primary classification models, the CNNs and LSTMs, are trained on a massive, diverse library that includes rare threats or edge cases the radar has never actually seen in the real world. It's absolutely vital for system robustness.
None of this advanced signal processing, from pulse compression through to deep learning, would be possible without the incredible advances in hardware. Specifically, the massive integration of functionality onto specialized chips and the exploration of new frequency bands.
The choice of operating frequency fundamentally determines what the radar can do. It's a trade-off between range, resolution, and the ability to penetrate things like rain or foliage.
We see a huge span of functionality across the spectrum. At the lowest end, you have HF, which is used for massive over-the-horizon detection because those long waves can follow the curvature of the Earth.
Then moving up, you have the LNS bands. They offer great range and are less affected by weather, making them the workhorses for long-range air traffic control and large-scale weather monitoring.
Then you hit the higher frequencies X, Q, and K bands. Their wavelengths are short enough to support small antennas and offer high angular resolution, which is why they're used for missile guidance, high-res mapping, and of course, police speed detection guns.
But the real revolution right now is happening in the M-wave bands, 40 to 300 gigahertz. At these extremely high frequencies, the wavelength is tiny, which enables phenomenal range and angular resolution over short to mid-range distances. Perfect for industrial and consumer applications.
And that's where the integrated chips come in, driving applications like autonomous vehicles.
Mm.
The processing is moved off huge racks and onto tiny pieces of silicon.
Exactly. You have companies like Texas Instruments with their popular million-wave sensors, like the AWR2243, operating at 77 gigahertz. These chips are a system-on-chip that performs much of the basic signal processing right there. And crucially, they often let users extract the raw ADC data,
Which allows researchers to bypass the chip's internal pipeline and implement their own custom, advanced MVDR or music algorithms.
Precisely. You also see NXP with chips like the MR3 Zen 3 focused entirely on 77 gigahertz automotive applications, and then Infineon's X10 SAV chip exemplifies miniaturization. It's a 60 gigahertz antenna in package design, meaning the sensor is complete and extremely tiny,
Low power consumption too, under 5 milliwatts in duty cycle mode.
which makes it perfect for low-profile applications like presence detection or the medical sensing we're about to discuss.
This shift highlights a fundamental engineering decision. Where does the heavy lifting happen? Is it on a dedicated processor like an ARM core,
Yeah.
or on specialized hardware like an FPGA?
That's the great hardware trade-off. An integrated processor like an ARM core found in something like a Xilinx Zinc offers flexibility. It's great for sequential tasks, high-level control, and running complex AI algorithms like LSTMs.
But the other option is the field programmable gate array, an FPGA, from companies like Lattice, which are highly optimized for parallel processing.
An FPGA, while less flexible, is absolutely essential for the foundational repetitive signal processing. Tasks like high-speed matched filtering, the range FFT, the Doppler FFT, they all need to happen in parallel at extremely low latency. An FPGA can execute these functions much faster and often with far greater energy efficiency than a general-purpose processor.
The ultimate illustration of this hardware and processing convergence is in a truly revolutionary application, taking radar out of defense and turning it into a tool for patient care through contactless vital signs monitoring.
This is genuinely game-changing. Using small, low-power millimeter-wave sensors like that Infineon chip we just mentioned, we can accurately monitor heart rate and breathing rate without ever making physical contact with the patient.
This has enormous implications, particularly for monitoring infants, the elderly in residential care, or diagnosing sleep disorders like sleep apnea, where traditional wired sensors can be uncomfortable or disruptive.
The mechanism is elegant and leverages the high-frequency advantage of millimeter-wave. The radar tracks the minuscule quasi-periodic motions of the chest wall, Breathing typically causes displacements associated with a very slow frequency range, about 6 to 30 breaths per minute.
These movements are tiny,
Yeah.
often measured in millimeters or even less. How can radar reliably detect something so small?
The key is phase sensitivity. The chest wall displacement directly modulates the received signal's phase, and the relationship is defined by a formula where the phase change is inversely proportional to the wavelength.
Ah, so a shorter wavelength means a higher sensitivity to movement.
Precisely. If we use a 60 gigahertz millimab wave radar, the wavelength is only about 5 millimeters. A displacement of just half a millimeter causes a large, easily detectable phase change. This extremely high phase sensitivity is what enables robust detection of these millimetric chest movements. It would be impossible with lower frequency radar.
So the processing pipeline we learned about has to be radically adapted for this medical application. We're not looking for a high-speed target. We're looking for a tiny movement on a stationary object.
We are. The data still goes through the standard range and Doppler pre-filtering. But instead of tracking a fast target, the system locks onto the dominant stationary range bin, which corresponds to the patient's chest.
And then the real challenge begins. Isolating the breathing motion from everything else, larger body movements, system noise, or slow phase drift.
That isolation is done by applying very precise, narrow bandpass filters, typically centered right around the expected respiration frequency of 0.1 to 0.5 hertz. These filters reject the large, slow movements and the high-frequency muscle twitches, leaving only the periodic breathing signal. Heart rate monitoring is even harder, requiring filters tuned to an even higher band.
The entire chain just demonstrates that the power of radar today isn't in its size, but in the precision of the processing algorithms that allow us to extract biological rhythms from the noise of the environment.
We've journeyed today from the devastating physical reality of that R to the fourth power drop-off, all the way to the level of algorithmic sophistication required to turn that whisper of an echo into actionable intelligence.
We started with the foundation, the necessity of pulse impression to defy the range resolution trade-off, and the utility of the range Doppler map to measure speed and separate moving targets from stationary clutter using MTI filters to remove those dangerous 0 Hz returns.
We then explored how spatial awareness evolved from slow mechanical systems to agile electronic beamforming. This paved the way for super-resolution algorithms like music, which use subspace decomposition to break the classical limits of angular resolution, albeit at a high computational cost that demands specialized FPGA processing.
And finally, we saw the modern frontier, treating the echo signal as visual data. CNNs classifying targets based on their unique microdoppler fingerprints, while LSTMs track temporal patterns for complex activity recognition. And all of it supported by JANs generating the synthetic data needed to stress test these AI models.
The primary takeaway remains. The limiting factor for modern radar performance is less about raw transmitted power and far more about the intelligence and speed of the processing chain. The difference between a high-power ARM system optimized for AI and a low-latency parallel FPGA is often the determining factor of whether an echo remains noise or is successfully transformed into a precise piece of knowledge.
We're already using these systems everywhere, from autonomous driving to diagnosing sleep apnea from across a room. The ability of radar to not just detect a target, but to instantly understand its identity, its intentions, and even its physiological state from a distance is only increasing. The next leap isn't just about making the sensors smaller, but making the AI smart enough to interpret the most subtle micro-Doppler signatures. How far away is the moment when radar can classify a threat or identify a person simply by the unique, subtle way they walk? That's the invisible evolution we are currently driving.